thank you to our villain vector. He told you that vectors are quantities that have magnitude and direction. Magnitude describes the length of our vector. Direction, self-explanatory. Since we are in our trigonometry unit, what do you think we're going to use to describe direction? That might be part of it. Trigonometry, what are we working a lot with? Because, Jackson, let me tell you, positive, negative isn't very specific. Okay. Angles. Angles will give us a specific direction for our vectors. Okay? Now, I have some pictures here for you about vectors that are equal or vectors that have common traits. Okay? So these two vectors are equal because they have the same magnitude and the same direction. These two vectors, however, have the same magnitude, but they have different direction. More specifically, what is true about their direction? They are opposites, which is creating that parallel effect up there. Okay? So we'll talk more about this later, but probably in tomorrow's video. But if our direction is the same or opposite, we have parallel vectors. Okay? But parallel doesn't always mean they're the same direction. All right, these two have the same direction but different magnitudes. Right, one's shorter than the other. And these two just have nothing in common at all. They have different directions, they have different magnitudes. Now, a lot of today is getting the basics down. Some of you are going to recall information from vectors very quickly. Some of you may think that this is the first time you're learning it, even though you have seen it before. It's just been that long. I don't know. But write down what you need to. But we're kind of speaking a new language. Okay, vectors, we're going to write them differently. We're going to talk about them differently. Okay. So a vector, we're obviously going to draw an arrow for. Okay. When we are in standard position, that means our vector is coming from the origin. Okay. We say that its initial point or its tail is at the origin. Okay. So when we draw a vector, we start at an initial point. And then the arrow that you have here, it ends at the terminal point. When that initial point is at the origin, we say that our vector is in standard position. Okay? And we are going to imagine our vectors in standard position. That yellow doesn't show up very well, so let me just go ahead and... That's it. Okay. So on our vector, where it begins is the initial point. Where it ends is the terminal point. We also call this the arrow, the head, like the arrowhead, right? That's the head of the vector, and this is the tail of the vector. When we write vectors, we are going to write them with numbers so that we can visualize them in standard form or draw them in standard form. Okay. We are going to have two different forms for writing vectors, but we're going to focus on one and talk a lot about vectors, and then towards the end I'll show you the other way we can write vectors. So this is what we call component form. Our initial point is what I have labeled as x1, y1, and our terminal point is what I have labeled as x2, y2. So if we know the two coordinates where our vector begins and where it ends, we can write the component form of the vector using this. Terminal minus initial for the x coordinates, terminal minus initial for the y coordinates. And instead of parentheses for a coordinate, we use the chevrons for a vector. So what you need to remember is terminal minus initial, okay, where it ends minus where it begins. And then, like I said, instead of like parentheses, to notate that it's a vector, we use the chevrons, okay? So go ahead and write down this example, and I think it'll make a little bit more sense as we go through this. We have an initial point of 2, -5, and a terminal point of -1, 3. Do you notice how U is bolded? When we name vectors, we name them with letters, and they are going to be bolded letters. So when I'm writing with my pencil or my pen, I just try to make it a little bit thicker writing if I'm naming it that. So our vector U, to get it in component form, which is what these chevron things mean, we're going to take terminal minus initial. So for our horizontal component, those are the x's, we're going to take terminal point -1 minus initial point 2. And then for our vertical component, that's the y component, we're going to take terminal 3 minus initial -5. So vector U is the vector -3, 8. Who can describe to me how to plot the vector -3, 8 on a coordinate plane? How about you turn to your neighbor and tell them? How would we plot -3, 8, the vector? Darby, how do you plot this?
Well, you'd want it to be in standard position, so you'd put the initial point at the origin, and then you'd move to -3, 8, and then that would be your terminal point.
So here's -3, 8, which is now our terminal point. And so there's our vector in standard position. Okay? I know some of us were talking about plotting those 2 points to plot our vector, but in standard position, this is what our vector would look like. Okay, so let's start talking about that whole magnitude and direction. Magnitude, we said, describes what of the vector? The length of the vector. Okay? So here I have a picture. No, don't have a picture yet. What I want you to write down first is that the magnitude is represented by this right here. It's the letter that names the vector with two absolute value bars around it. That means magnitude. Okay, I'm going to draw a vector. And the length of this vector, we call the magnitude of v. Okay, now let's talk about how we plotted that -3/8 back here. If our vector was -3/8, we went horizontally 3 and then vertically 8. Do you agree? So we have these horizontal components and vertical components. So let's say our vector is the vector AB. Okay. That would mean our horizontal component is A and our vertical component is B. Will, if you were to guess, what mathematical concept are we going to use to figure out the magnitude? The law of sines. We could even make it more simple. What kind of angle is this right here? So what can we use? Regular. Okay. So if we know A and we know B, what do we need? 50? Okay, sorry, you were kind of mumbling. Pythagorean theorem, is that what you said? Hey.
You said right triangle trig.
Right triangle trig. Pythagorean theorem falls into right triangle trig. You did say right triangle trig. Okay. We know that a squared plus b squared would have to equal the magnitude squared. Do you agree? Therefore, the magnitude is just the square root of a squared plus b squared. We like the Pythagorean theorem, right? Our previous example was the vector -3/8. If we want to find the magnitude of the vector -3/8, then all we have to do is take the horizontal component squared plus the vertical component squared and square root that quantity. Connor, what's our magnitude? So square root of 73. And I want you to leave it like that. Okay? Reduce it if you can, but go ahead and leave it as a radical. Okay? Now I know a lot of you are going to be ready to talk about the direction. But we're first going to take a moment and we're going to talk about combining vectors together using addition or multiplying by a scalar. Okay? So don't write this down right now. What I would write down is that the sum is the same as the word resultant. That is a vector word that's going to be thrown out. Okay? And there's two different ways that we can look at this pictorially. Okay? There's going to be parallelogram addition, and then there's tail to head addition. So before lunch, I want to draw you a picture of those. So this is what parallelogram addition is for u plus v. We have our vector u, and we have our vector v, and they are graphed both in standard position. If we create a parallelogram out of those two vectors, then the diagonal in standard position would be u plus v. Tail to head addition is one that I visualize better. You may visualize parallelogram better, and you can decide which one you want to use. All right. Tail to head means for u plus v, you're going to plot u in standard position, but then at the head of u, you will begin the tail of v, and then you would connect them for u plus v. So you get the same vector, it's just two different pictures to get there. Okay? When we come back from lunch, we will look at what it looks like with numbers. Enjoy your food. All right, so here are our visualizations for adding two vectors together. Like I said, I don't care which one you use, but you will have to draw one of these in your homework tonight, okay? Which one you use, up to you. Let's go ahead and attach some numbers to it. So write down that vector u is 2, 3, and vector v is 4, 1. If I wanted the vector u plus v, Kelsey, what would you tell me? What do you think we should do to add these together? Draw the picture? Okay. So we have the vector 2, 3. And then we're going to add the vector 4, 1. So our resultant is the vector 6, 4. Without drawing the picture, describe to me how we get that vector. Okay, add the horizontal components to get 6, add the vertical components to get 4. U minus V. Molly, what vector would that be?
Can you subtract the u and the v from the x and the y's?
Yeah.
Oh, so 2, oh wait, -2.
So -2, 2. Good. -2, 2. You can just take the first one and subtract the second one. Keep the horizontals together, keep the verticals together. Now, let's talk about what this picture would look like. We have the vector 2, 3. And then when we subtract v, that's like adding the opposite. So we would plot the vector -4, -1 to add with it. So that's u, that's -v to get our vector -2, 2. And we would add the opposite, which is what subtracted. Lastly, I want the vector for v. If v is the vector for 1, Connor, what is 4v? Yes. Okay. Multiplication is just repeated addition, all right? So if we wanted to plot this one, we would just have 4 v's to string together. Okay. So we can add vectors together by combining their components. We can subtract vectors by subtracting their components. And we can multiply by scalars. We call this 4 a scalar. It's kind of like your coefficient, right? Friday, we'll talk about multiplying vectors together, but right now we're just going to focus on taking a scalar multiple of a vector. Okay? Now, I don't think you need to write these down. We're just going to talk about them. These are some properties of scalar addition and, vector addition and scalar multiplication. So let's just kind of talk through these because a lot of them you're going to say, oh yeah, I would have assumed that anyway. All right? Vector addition is commutative. It doesn't matter the order in which you add, you're still going to get the same vector. Some of you probably already assumed that anyway. Okay? Vector addition is associative. It doesn't matter if you have 3 vectors added together. It doesn't matter the order. They're still going to add to be the same vector. This 0 that's bolded, that's a 0 vector. So the vector 0, 0. If we add a vector to the 0 vector, we still have the same vector. Adding a vector to its opposite will get you the 0 vector. Over here, this is just saying if we have 2 scalar multiples, it doesn't matter what order you do the multiplication in. Okay, so it's kind of associative property with multiplication. What property is number 6? Distributive. Okay, scalar multiples can be distributed. Same thing with number 7, right? Number 6 is distributive where we have 2 scalars being added. Number 7 is distributive where we have 2 vectors being added and we distribute a scalar through. Do you see how the scalar is not bolded? Okay. 1 times a vector is itself, 0 times a vector is 0. And then number 9, if we have a scalar multiple to a vector, then we can take the magnitude of the vector and multiply by that scalar's absolute value because the magnitude always has to be positive. Okay, you may not use any of these properties, but they're there for you on one of your pages. I don't remember what page. But you can get by with this whole assignment without knowing these off the top of your head. Okay. So let's talk about direction. You spent all lunch just wondering how are we going to find the direction. So first of all, the direction angle is always going to be measured from the positive x-axis. That sounds familiar, doesn't it? An angle with a positive x-axis. That's how we measured angles in chapter 4, isn't it? So I have the vector v drawn up there. and its component form is AB, and our direction angle is theta. So we know how to find the magnitude, square root of A squared plus B squared, but what we're going to determine is how to find that angle theta. So here's my question. If we know that the horizontal component is A, and we know that the vertical component is B, turn to your neighbor. What could we use in right triangle trig will to determine theta? You have 10 seconds. Turn to your neighbor. What could we use? If we know A, we know B. Okay, how do we determine theta? What do we use? Tyler? The tangent of theta is going to equal B over A. That is exactly what we are going to use. Tangent of theta is opposite over adjacent. You can either remember that or use your picture to do it. Okay, because in chapter 4 we did this quite a bit. Okay? The only stipulation I will make is make sure that the quadrant matches where your vector is located. If your vector is lying in quadrant 4, you better have an angle between 270 and 360. If your vector is in quadrant 2, you better have an angle between 90 and 180. So we're going to have to use our calculator and our brains combined to get this angle. All right, so we'll start off with a simple example. The vector 5, 4. Here's a vector 5, 4. We want to know the direction angle. So we know this adjacent side is 5, the opposite side is 4. So we know that the tangent of theta is 4 over 5. In your calculator, please take the inverse tangent of 4/5. You know what? We're going to go ahead and just stay in degrees since the rest of the chapter we've been in degrees. It'll be a nice change for us. Jackson, what do you get?
38.66 degrees.
Can anyone confirm that? Thank you. Does 38.66 degrees make sense for our vector? It does, because it's in the first quadrant, right? Does anyone feel like this is like really familiar? Right? I mean, we're doing all the stuff we did in chapter 4 just with vector, right? Okay, now let's go back to our first example. -3/8, right? Okay. Now, technically, this is the direction angle that we want, but in our calculators, we're probably going to get that angle, right? So let's just say, you don't even draw a picture, you just say, I know that the tangent of our direction angle is B over A. If you type in the inverse tangent of B over A, what do you get? Will you say that letter?
I get 69.443.
negative 69.43. Is that our direction angle? It is not. Okay? Our vector lies in the second quadrant, which means we need a second quadrant angle. So this would be my suggestion. I wouldn't even worry about that 3 being a negative. I would really just find the inverse tangent of 8/3. And that is going to give you your reference angle. Okay? So Gabe, how do I get that second quadrant angle? We're going to take 180 minus the 69.43 degrees to get a direction angle of and that makes sense for our second quadrant angle. Vector. If you remember back to chapter 4, the inverse tangent feature is only going to give you values between negative 90 and positive 90, which means you're always going to get an acute angle in your calculator. So if you are not in the first quadrant with your vector, you're going to have to do some sort of calculation with that reference angle to get the correct direction. Now, if it's in the fourth quadrant and you give me a negative direction angle, I mean, technically that would be fine unless I specifically ask for a positive one. Okay. Any questions about that? Okay. We worked on the unit circle. Why was it called the unit circle? Because the radius was 1. So what number do you associate with unit? 1. We have what's called a unit vector. And a unit vector means our vector has magnitude of 1. Okay, now I'm going to come back to this picture over here. This 4V picture. 4V is a scalar multiple of V. What's true about their direction? They're the same. If we take a vector and multiply it by a scalar, the direction isn't going to change, only the magnitude is going to change. So 1, 1 and 5, 5 are in the same direction because they're multiples of each other. Okay? Unit vectors can be very beneficial for us. And so what we're going to do is we're going to take a vector and we're going to force it to be a unit vector in the same direction. So by saying the same direction, we're just going to multiply it by a scalar. And specifically, to get it to be a unit vector, we're going to multiply by that scalar. So by taking 1 over the magnitude and multiplying it to our vector, we have created a unit vector that will still have the same angle as vector v. So the example that we are going to work with is the vector -2, 5. So go ahead and write down v equals -2, 5. And what I want you to do is I want you to calculate its magnitude for me. Remember, I want the magnitude to be kept as a radical. Then what do you have for your magnitude? Finn has radical 29. Do you agree? Okay. 2 squared is 4. 5 squared is 25. We have radical 29. Okay. So if we want a unit vector, we are going to take 1 over radical 29 and multiply it to the vector -2, 5. So what I'm going to do is I'm going to go ahead and rationalize the scalar to radical 29 over 29. And then what we can do is we can multiply that through. If we were to go and find the magnitude of that vector, it would have magnitude 1. Last concept. We just talked about a unit vector. We have 2 standard unit vectors. This is what I want you to write. I is the vector 1, 0, and j is the vector 0, 1. This is I as in vector I. It is completely separate from imaginary number I. I is vector I. Here is where we get a second way to write our vectors. The vector 2, 3 can also be written as a linear combination of I and j. So 2 times I, because 2 is the horizontal component and I is our horizontal unit vector, plus 3, because that's our vertical component, multiplied to j, our vertical unit vector. So 2, 3 in chevrons is a vector in component form. 2i plus 3j is a vector in linear combination form. It's just 2 different ways to write a vector. They still mean the same thing. am not here the next 2 days. But what I have done for you is I have put my workout solutions to tonight's homework, tomorrow's homework, and Friday's homework on my website, evens, odds, everything. So if you have trouble, you can reference that. Each day you come in here, the sub will give you 5 to 10 minutes to talk about homework. So if you have an issue, you're asking someone in here. If someone needs to go to the board, you do it. Okay? There will be a video each day, homework at night, that is on my website. Friday, you will get a take-home quiz that is due on Tuesday. Okay? There will be a review that you can take if you want, where my solutions are already on my website if you need extra practice before you complete your take-home quiz over spring break. Are there any questions about how that's going to go? I know, spring break is exciting, right? Now,